Good morning, everyone. Thank you for being here. My name is Gabor Kuruc, and today I will present our work on application-aware user-playing function placement for low-latency 5G and 6G services. This is joint work with colleagues from the Budapest University of Technology and Economics. Let me start with the motivation. Fifth and sixth generation mobile networks host increasingly diverse services. Think about interactive extended reality, teleoperation, closed-loop cyber-physical control, or large-scale industrial IoT, all with very tight end-to-end latency budgets. Multi-access edge computing has helped by bringing compute closer to users, but the fundamental question of where exactly to place user-playing gateways and application components for each service remains largely unsolved. Today's practice is slice-centric. We differentiate enhanced mobile broadband, ultra-reliable low-latency communications, and massive machine-type communications, and then optimize latency within those labels. The problem is that this treats all traffic within a slice as homogeneous, ignoring how different applications actually generate responses and where latency accumulates. As a result, a placement strategy that minimizes a generic aggregate latency might still fail to meet the quality of experience target of a specific service, because it minimized the wrong segment of the latency budget. The core insight of our work is that end-to-end latency has structure. It is not a single monolithic number. For any service request, we can decompose the delay into three main interactive paths. First, DCP, the client proxy delay, the round-trip time between the user device and the nearest application proxy. Second, DPP, the proxy-proxy delay, latency incurred when two application instances need to coordinate with each other. For example, in a multi-user VR session where two players must synchronize their state. Third, DPD, the proxy database delay, the round-trip time to a shared state component such as a database or key value store. The crucial observation is that different services are dominated by different components. A VR collaboration session is sensitive to proxy-proxy latency. A simple sensor query only cares about client proxy delay. A streaming dashboard needs both fast front-end and reasonably fast state access. Therefore, placement decisions must target the dominant latency leg for each service, not just minimize an undifferentiated aggregate. Let me give you a quick roadmap of our contributions before diving into the details. We make four contributions. First, a service classification framework, a simple taxonomy of three service classes based on how applications depend on coordination and shared state. Second, a formal latency decomposition model, and from it, three canonical deployment archetypes for MEC-enabled 5G and 6G systems. Third, concrete orchestration guidelines, practical placement rules that tell you which latency leg to target for each service class. And fourth, a numerical evaluation on a stylized synthetic topology demonstrating that service-aware placement not only reduces mean delay, but also reduces delay variability, which is equally important for real-time applications. Importantly, the framework is designed to complement existing slice-based orchestration. Now let me present the formal model. We consider a 5G and 6G edge-enabled architecture where user equipment traffic is anchored at a UPF and steered toward application logic at MEC sites or, if necessary, toward a core or cloud location. Application logic includes a lightweight proxy for session management and caching, and an optional state component such as a database. The end-to-end delay for a service request R decomposes as D of R equals D capital CP plus D capital PP plus D capital PD plus D process. Rather than minimizing this aggregate, we introduce a service-aware objective J capital S that weights each component according to how strongly it affects perceived quality for service class S. The weights WCP, WPP, and WPD are non-negative and service-specific. The key point is that minimizing the total delay D does not generally minimize the service-specific objective JS, because the dominant weight may be on a component that a generic placement strategy does not specifically target. Based on the model, we define three service classes. Class 1 is independent services. Each request is self-contained. No peer coordination, no latency critical state access. The client proxy weight dominates, so placing the proxy as close as possible to the user is the primary objective. Typical examples are simple sensor queries and stateless API calls. Class 2 is background synchronized services. A user-visible response can be generated locally, but the system still needs periodic or asynchronous access to shared state. Both client proxy and proxy database weights are relevant, but proxy is negligible. Examples include IoT monitoring dashboards, content discovery, and collaborative editing with optimistic local responses. Class 3 is real-time coordinated services. The user-visible response cannot be generated at a single proxy because it requires tight, continuous exchange with peer proxies or coordinated application instances. Proxy delay dominates. Examples are multi-user VR, teleoperation, distributed robotics, and crowd-assisted gaming. This classification is intentionally lightweight. It provides a decision-oriented abstraction rather than trying to capture every application nuance. Here is a summary table of the three classes and their dominant latency components. For independent services, DCP is dominant and the others are negligible or minor. For background-synchronized services, both DCP and DPD are important. For real-time coordinated services, DPP is the dominant driver, DCP is still relevant, and DPD is secondary. This table is the key design map for the placement rules I will describe next. We identify three canonical deployment archetypes that correspond to progressively richer edge footprints. Archetype A1 is UPF only. The user plane anchor is at the edge, but application logic remains centralized. This is the current default for many deployments. Archetype A2 adds a lightweight application proxy co-located with the UPF at the MEC site. This directly reduces client proxy delay, and if interacting users are served by the same edge domain, also reduces proxy delay. Archetype A3 goes further by additionally deploying a state replica or cache at the MEC site, reducing proxy database delay. The trade-off is increased storage cost and the need to manage state consistency across replicas. Importantly, these archetypes are software deployment patterns over a fixed MEC infrastructure. They do not require changes to the physical network. Now let me map the service classes to the archetypes. For independent services, A1 or A2 is sufficient. A2 is preferred when a local proxy can serve cached content and reduce client proxy latency. Adding a full database replica, archetype A3 provides only marginal benefit because state access is not on the critical path. For background synchronized services, A2 reduces front-end delay and A3 becomes attractive when state access is frequent. Note that we do not need strong real-time consistency here. Eventual consistency or partial replication of hot data is usually enough. For real-time coordinated services, the most important design decision is to cluster interacting proxies within the same MEC domain, which suppresses the costly cross-edge proxy path. A3 is only worth the cost if state access is actually on the real-time interaction loop. I summarize these as three simple placement rules at the bottom of the slide. A brief word on how this framework can be implemented in practice. The archetypes A1 to A3 are software deployment patterns. Virtualized or containerized workloads managed by NFV, Mmano, or Kubernetes-based platforms over a fixed MEC infrastructure. There are two relevant timescales. On a slower timescale of minutes to hours, operators can pre-provision edge clusters and select which sites operate in which archetype based on observed service demand and resource availability. On a faster timescale, the control plane makes per-session anchoring and clustering decisions among already deployed instances. No new infrastructure is needed. Crucially, our framework is complementary to existing slice-based management. Slicing still enforces isolation and high-level QoS. Our service classifier adds a lightweight additional signal indicating which latency leg matters most. An SDN or NFV orchestrator can consume this signal to refine placement decisions. No per-packet reconfiguration is required, and operators can adopt the framework incrementally. Let me describe the evaluation setup. We use a small synthetic topology consisting of 8 access cells, 2 MEC sites, Edge A and Edge B, and 1 core site. Cells 1 through 4 are in Edge A's domain with 1 millisecond one-way latency, and cells 5 through 8 are in Edge B's domain. Cross-domain latencies are 4 milliseconds from a cell to the far edge, 5 milliseconds between the two edges, and 9 milliseconds from each edge to core. To obtain non-degenerate delay distributions without a full queuing model, we augment each path with a utilization-dependent penalty and a small uniform jitter. We generate 5,000 samples per workload across 50 time slots. The baseline slice-centric strategy uses archetype A1, core-hosted, for independent and background synchronized workloads, and A2 for coordinated workloads. The service-aware strategy uses A2 for independent, A3 for background synchronized, and A2 with proxy clustering for coordinated services. I want to emphasize that this topology is intentionally stylized. The goal is to illustrate structural effects, not to reproduce a specific deployment. Let me present the results. For independent services, service-aware placement, archetype A2 with a local proxy reduces mean delay from about 28 milliseconds to about 10 milliseconds. That is roughly a 63% reduction simply by moving the proxy to the edge instead of leaving it at the core. The standard deviation barely changes in both cases, indicating a well-localized, consistently fast service regime. For background synchronized services, the picture is very similar. Again, about a 10 millisecond mean under service-aware placement versus 28 milliseconds for slice-centric, with low variance in both strategies. These two classes primarily serve as consistency checks for the model. They confirm that the expected delay range shift occurs when we target the right latency leg. The more interesting story is in the coordinated class, which I will show next. Now the key result, real-time coordinated services. Under service-aware placement with proxy clustering, the mean delay is about 11.7 milliseconds, with a standard deviation of 1.5 milliseconds. Under the slice-centric baseline, the mean rises to about 19.3 milliseconds, and the standard deviation explodes to 9.1 milliseconds. That is a six-fold increase in spread. The reason becomes clear when you look at the bimodal distributions in the figure. Both strategies produce a bimodal distribution, reflecting two structural regimes, same edge pairs with low proxy-proxy delay and cross-edge pairs with high proxy-proxy delay. The slice-centric strategy leaves both modes present, with the upper mode centered around the costly cross-edge path. Service-aware proxy clustering eliminates the cross-edge regime by ensuring that interacting users are served by the same MEC domain. The gain here is structural. It is not just about reducing an average number. Placement fundamentally changes the communication regime, and for services like teleoperation or collaborative VR, this reduction in variability may be more important than the reduction in mean delay. This figure shows the empirical delay distributions for the real-time coordinated service under both placement strategies. On the left or in the upper panel, you see the service-aware placement with proxy clustering. The two modes are close together, both in a low delay regime, and the overall spread is tight. On the right or lower panel, you see the slice-centric baseline. The lower mode is at a similar position, but the upper mode shifts far to the right due to the cross-edge coordination penalty, creating a very wide spread. This visualizes the structural difference I described. Service-aware placement suppresses the high delay regime entirely. Let me now discuss what these results mean more broadly. The main message is that service dependency is a useful orchestration signal that goes beyond the coarse granularity of slice labels. For each class, there is a clear primary lever. For independent services, it is client proxy proximity. For background synchronized services, it is also managing state access, and for coordinated services, it is proxy clustering. A second important point is that placement affects not only mean delay, but also delay variability. By localizing traffic, service-aware placement reduces load on shared inter-edge and core segments, narrowing the effective delay spread. For interactive services where temporal consistency matters, think VR or teleoperation, this can be as important as lowering the average. I should also be transparent about the limitations. This is a stylized evaluation on a small topology with a simplified load model. Real MEC deployments may have multi-level hierarchies with local, regional, and central layers, which is a natural extension for future work. To conclude, slice-centric placement is too coarse a signal to capture the latency structure of emerging 5G and 6G services. We proposed a lightweight service dependency-aware framework that classifies services into three categories and maps them to deployment archetypes with actionable placement rules. The numerical evaluation on a stylized topology shows that service-aware placement not only reduces mean delay by up to about 60% for the simpler classes, but also dramatically reduces delay variability for real-time coordinated services by a factor of 6 in standard deviation. The mechanism is structural. Proxy clustering eliminates the costly cross-edge interaction regime entirely. Looking ahead, a natural next step is to embed the service-aware performance objectives JSUBs into a formal multi-objective placement optimization for a heterogeneous service mix. Extensions to hierarchical edge architectures, richer load models, and multi-operator settings are also planned. Thank you very much for your attention.